So now that we've seen how to estimate a regression equation and to draw some relevant charts, let's have a look at how to carry out some standard specification tests and diagnostic tests. So one thing you might often want to look at, of course, when you've estimated an equation is to test some linear restriction on the coefficients of your independent variables. For example, you might want to test that two or more coefficient values are jointly equal to 0. Now you can do this with either this f-test function here or the wall test here. Both operate essentially in the same way. Now if you look at the stats model web page on this f-test function here, this tells you how to implement this. There are two ways. The easiest way is to simply specify here in brackets after f-test a expression in inverted commas which states what you want to test. So here this is a test that the coefficient on x2 and x3 are both jointly equal to 0. And that's the easiest way to do it. However, that doesn't always work, as we'll see in the case that I looked at. The alternative way is to specify the R matrix in the little matrix equation here for testing linear hypotheses, linear restrictions. Now, if you've done this before, you'll have probably come across this little matrix equation here. Beta is, of course, the estimated coefficients, and then R is a matrix which indicates the restrictions. So, for example, in the case of this one here, you need to set up a matrix R, and you do that by specifying each row in turn. So this first row has a 0 and then a 1 and a 0 and 0. What that says is that the second, this variable here, x2, is the first variable, and you, because this 0, I think, is the intercept, and you're stating that you want that coefficient on that to equal 0, but you're ignoring the others, hence the noughts. And hence this one has a 1 in the next position for the x3, and noughts in the other ones. So you can see how to set that up. You'll find in any standard econometrics or statistical textbook, it will tell you how exactly this is done, but that's basically what you're doing. So you set up that matrix, you then turn it into an NP array with this function here, np.array, and then you put that matrix R, this new array, into the f-test. And as you can see, you get the same result in both cases. Now, clearly this looks easier, but this may not always work. For example, in the case here where I wanted to test that the coefficients on income and income squared were jointly equal to 0, that method here wouldn't work. It wouldn't accept, I tried to put in income equals income squared equals 0. It wouldn't accept it. I had to do this method here. And in fact, I think this method is better if you want to test some a sort of more linear restriction on the coefficients. For example, testing that two or more of the coefficients add up to a given number, something like that. You need to set up this R matrix. The details of how to do that, you say, you'll find in any statistical or econometrics text, such as Green. So here I'm using this. I've set up the R matrix. Now remember, we've got essentially 5 variables here. If we include the intercept, we just look at the equation again. Here we've got 1, 2, 3, 4, 5. So this one is intercept is the first one, and then that one and that one. So I want to for this one I need to put 0, 0, 0, 1, 0. And for this one I need to put 0, 0, 0, 0, 1, which is what I've put here, as you can see. And so that's testing whether the coefficients on those two variables are both equal to 0 jointly. So I've set that up, I've turned it into an NP array, and then I've put it into the f-test, and here are the results here. Okay, so you get the f-stat, then the p-value. It also gives you the degrees of freedom in the denominator and numerator. If you know how to actually calculate this f-statistic, you'll know what those mean. But and of course, you could always have done this manually by estimating the restricted equation and then calculating the f-statistic manually, but this is quicker. If you want to use a Wald test instead for a large sample chi-squared test, well, it's the same, basically the same. You use the Wald test function in this case. Again, put in that matrix R, but this time you need to set these two options, these two parameters. Use f equals false, otherwise you get the f test, and scalar equals true. And if you do that and run it, you'll get this result here. So here's the f test, here's the chi-squared test. Obviously they're given the same answer, that this restriction is rejected. Now, these sort of specification tests, of course, do assume that the standard errors are correct, that you've got no problem with heteroscedasticity or autocorrelation in the residuals. Now, we need to test for that, of course, before we start running these tests. So there are some standard tests. Now, one test for heteroscedasticity is, of course, to look at a chart like this, residuals against fitted values, which we plotted previously, and that does indicate some potential heteroscedasticity here of a non-constant variance. And in fact, this data does in fact have heteroscedasticity, because, as I mentioned, it's taken from the chapter on heteroscedasticity in Green's textbook, so it's not a surprise. But of course, this is only suggestive. We need to run some actual statistical test. Now, there are a number available, and stats models enables you to carry out all of them. The most common one is the Breusch-Pagan test, which you can run using this function here. Now, it's quite long. It's in stats models, so you put sm, and then it's .stats.diagnostic.het underscore Breusch-Pagan. You don't have to remember type all this out. If you start typing it, and then it will recognize what you want ultimately, and that will help you to put it in, but it's quite long. Now, if you want information on that, of course, you can always press Shift Tab or go to the stats model website and look this one up, and here it is. So this does the Breusch-Pagan Lagrange multiplier test for heteroscedasticity. You need three parameters: the residuals of your model, then an indication of which independent variables you think are suspected of being related to heteroscedasticity. And there's also this option here which has a default value of true. With the default value, you get what's called the Coenca, or also known as the studentized version of the test, which is the more one most usually used these days, which assumes independent and identically distributed error terms. If you want the original test, you set this option, robust, equal to false. So here is the code here. So there's the function. So we put in the residuals. Remember, we saw how to get those from our variable containing the results. It's dot resid. Now, to specify that you want to use income and income squared, which is what I'm looking at here, as the exogenous variables, I've used this property here, model.exog, on my, which is a property of my results variable, because that returns the data, the exogenous variable matrix. And to specify the columns, you put in as a list here a colon, a comma, and then as a further little list, so in square brackets, naught, which is the intercept, comma, and then 3, because remember income was the third, as we saw up here, the third variable. Remember that we count from 0, so the intercept was 0, 1, 2, 3, and then income squared was 4. So counting down from here, that's 0, column 0, column 1, column 2, column 3, column 4. So I need 0, 3, and 4. You must include an intercept. So I think you can see how I've done that here. And then if we run that, we'll get the results like that. Now, it's not a particularly nice printout here because it's not clear what, it doesn't tell you what each one means. So that's why you have to look at the web page here. So what it turns, the first value is the Lagrange multiplier statistic, the chi-squared statistic, and then the next one is the p-value for that. It also gives you the f statistic and the f value, but these are the two that you need to look at, the first two. So we've got a chi-squared at 6.18 and then a p-value 0.05. Now that's not, that is rejecting the assumption of homoscedasticity. That's the null hypothesis. So we have got heteroscedasticity problem here. This was the studentized or Coenca version. If you want the original version, just set robust equals to false and run that, and we get the this one again. Here's the chi-squared statistic. Here's the p-value. So here again, it's clearly indicating that our null of homoscedasticity is rejected. We might also want to have a look at a histogram of the residuals. So I've shown that here. I've used this histogram function before, like that. Now, are these normally distributed? Well, remember that the Jacques-Berer test of that is part of the standard printout here. If you want to run it separately, because there are other options that you could put in, just use the Jacques-Berer function here, which is in sm statmods.statstools.jacques_Berer, and just put the residuals in. This will just give me the same results as we had up here in our standard printout. Now, so we've got heteroscedasticity. How to deal with that? Well, typically there are two ways. The way that it was often done previously was to re-estimate the equation allowing for the heteroscedasticity by using something like weighted least squares. I think a more modern and more usual approach these days is simply to calculate what are called robust standard errors, a robust covariance matrix, which takes into account the heteroscedasticity. Again, if you know the econometrics here, the statistics, you'll know what I'm talking about. Now you can easily estimate, get results using robust standard errors, using this function here, get_robust_cov_results, which is in stats models. You run it on your variable containing the results of your regression, RES in our case here. And then in brackets, you put firstly which of the various robust covariance matrices that you want. Again, if you've looked at this, you'll know that there are a number available, which HC stands for heteroscedasticity consistent, and there's 0, there's HC1, there's HC2. You'll need to consult something like Green or some other text to find the difference. If you look at the help system, it'll tell you a little bit about these. These are heteroscedasticity, difficult to say, consistent covariance matrices, often just known as robust covariance matrices. HC0, 1, 2, 3 seem to be the ones here. Again, if you look at the stats model web page on this, it'll tell you some of these ones here. So they're all pretty much the same. It depends which one you want. By default, it looks as if it gives you HC1. Yeah. So if you don't specify this type parameter, you'll get HC1. I've used HC0 here just as an example. And that returns the same results as you had here, but it will use robust. This will say robust here, the covariance matrix, so it will, which is allowing for the it's correcting. It's a form of correction of the standard errors to take account of the heteroscedasticity, which means your t-values are going to be better. I'm not sure it means that they're absolutely totally accurate, because you're not removing the heteroscedasticity as such, but they're much more they're consistent. So with a large sample, they should be okay, which means your t-values are correct and so on. So you simply run that. Don't think, and then you ask for a summary as we did before. And as you can see, you get the same printout, except you now have it's using these robust standard errors. So you can look now properly at the t-stats and run f-stats, f-statistics, and so on. Okay, so that's often what is now done these days, but another way that used to, I think maybe still done, but it's not, I don't think it's quite as common these days, is to re-estimate, allowing for the heteroscedasticity, in effect removing it. A standard way that has been used for that is what's called weighted least squares. So I'll mention quickly how that is done here. You simply use the WLS function rather than the OLS. Again, notice the capitals that's in stat models. So you set it up in exactly the same way as we did with OLS. So it's sm.wls, and then in brackets you supply those two matrices again, y and x, but this time you specify this option here, weights equals, and then you indicate the weights. Now if you assume that the error term is proportional to income, which is one of the standard assumptions when you use weighted least squares, then the weights are 1 over the income variable. So you simply put that. Notice here I've used the X matrix and indicated the income variable. So you run that. That then goes into a variable which you then apply a fit function to. Obviously you could do that in one go, but here it's best to do it separately. And then summary. So basically this is the same three statement syntax as we use for OLS. The difference is it's WLS, and you have to specify the weights. So running that, we get the same printout as before, the same information, but this time it's estimated weighted least squares. Now, of course, you could then look at a printout of the residuals against fitted values to see if that's improved matters. In fact, it doesn't look as though it has, particularly here. Of course, you could run the Breusch-Pagan test again. Let's say you decide, therefore, that the error term is proportional to income squared rather than income. Well, again, same syntax, WLS, y and x, then set the weights as 1 over income squared. Now, notice again here, I tried putting simply 1, as I've done here, simply put 1 over and then x, and in brackets income squared. It didn't seem to like that, so I resorted to using the model.exog matrix, which is returned as part of the results. Remember, we saw how to do that up above, how we use that up above. And I specified just column 4. Don't forget the colon, comma, and then in square brackets the column you want. So that's specifying column 4, which is, as we've seen, is income squared. So it's 1 over that. And then we get results of that. Again, we can then check the fitted values against residuals to see if there's any improvement. Again, I don't think there is particularly. Of course, you could run again a Breusch-Pagan test So that's how you'd carry out weighted least squares if that's the approach that you take to the heteroscedasticity problem. But I say what I think mostly occurs these days is that people simply calculate robust standard errors using one of these covariance matrix, these heteroscedastically consistent covariance matrices, HC0, HC1 or whatever. Okay, so that shows you how to carry out specification tests, diagnostic tests, and weighted least squares, which is most of the sort of techniques, the things you'd be doing if you're analyzing cross-section data. There are other things, of course. I haven't covered everything here, but I think that shows you how you can, these two videos have shown you how you can use the stats models package to do all the sort of standard econometrics, statistical regression type work that you would need to do. It's a very, very good package. I say there's lots of other features in it besides, as you can see here, besides ordinary squares, the generalized quantile regression, pretty much any standard statistical procedure you can think of is probably covered here. So it's a very, very good package to get to know.